All right, you guys ready to get steamrolled? I'm gonna give away gold right here. This is gold. Maybe not exactly. So, just to get up on my soapbox for a second, there's a particular mechanism that I think we could employ to do a lot of people on planet Earth a lot of good, to give them a little bit of energy and a little bit of water security. And I've been mentioning this throughout the course of the semester, but I just thought I'd give you a little proof of concept here. So what I want to do is take a solar-driven steam engine and couple it to a water purification system. Essentially take your gray water, feed it through the steam engine, let it gas off the water, give you a distilled water byproduct that hopefully is drinkable, and you can do all kinds of other things with it. You could couple this system to a central heating system in a house, and so the thermal energy generated, the waste heat can be utilized downstream, blah, blah, blah. But essentially, all you need is solar focusing, some kind of a solar focusing technology, and then a steam engine with water as the working gas. Here is a little YouTube video of some people that have constructed a solar steam engine. There's a lot of surface area that they're using. The sunlight's landing on those mirrors and they're focusing it at the top of this tower, kind of like they do in those solar towers that we showed you. But I wanted you to get a visual for how much energy and how much water this thing will kick out. I'm going to show it here in a second. It doesn't have to be this big. This is just their working model. See this down here? You see that stream of cloud? You know what that is? That's the gas. You know, after the steam goes into the chamber, it expands the piston and it gets released. Well, that big stream of cloud that you saw, that's all the gas phase water being let out. And look at that power that's being generated by that motor. That's a lot of power. That could do somebody out in the third world or the desert somewhere a lot of good if they had batteries that they could use to store that power. So just FYI, there's a pretty direct path to clean water and cheap energy via solar steam engines. There's a few different research groups that are working on these concepts, but as far as I know, no one's really yet developed and employed a working system for residential type water purification and energy. I think that needs to be done in the future. All right, now here's the part where you really get steamrolled. We're going to be working through some things fairly quickly, fairly rapidly again. Today what we're going to try to do is instill the key points and concepts that need to be understood in order to understand rates of reactions. And so rates of reactions are functions of many different things. We're going to find out they're functions of concentration of reactants. They're functions of something called the activation energy, which is the energy barrier to a reaction. They're functions of temperature. And they're also functions of the three-dimensional geometric constraints on a reaction. And we're going to try to illustrate all of those things today. We're going to be going a little bit deeper than you'll actually be required to go for the course of exams. But hopefully after we show you all of it, you'll have a good working knowledge. So to get into this, we're going to use a for instance problem. In this for instance problem, I'm looking at a diatomic molecule AB that has a single covalent bond between the A and B atoms, 2 electrons shared in that bond. And this molecule is going to react with this free atom C that has an electron in its valence shell that wants a pair, right? Now, the products, the possible products are B bonded to C. We're going to assume, for the sake of this example, that A atom and C atom do not react to form a bond. And so essentially what wants to happen is this C atom wants to grab a hold of one of these shared electrons, pull it over into its valence shell, and with it, it wants to bring the B atom. This is going to require that this AB bond be broken, and that's going to be easier said than done. The thing about this AB bond is that it has electrons that are in kind of low potential wells, and so they're kind of tightly bound, they're closely attached to the nuclei that they're associated with, and when they're closely attached, remember those forces are really strong. The closer you are to the nucleus, the stronger the forces. And so those electrons aren't going to come out very readily. And we're going to look at what has to happen in order for those electrons to come out. First of all, we need contact. We need the two species, the C atom and the AB molecule, to approach each other. The C atom has to get close to the AB molecule. It's the kind of electromagnetic fields that are emanated by the C nuclei that are going to attract that electron, and they can't do it unless the C atom approaches. So we have this requirement that the C atom has to get close to the AB molecule and the bound electrons. There are requirements, there are constraints on the angle of approach. So, get this whole thing in here. Or the direction of approach. Your C atom wants to get a hold of these electrons in the AB bond. It has to approach those electrons. In this case, I've shown the C atom approaching the AB molecule from the A side. If that's the case, if the C atom comes up and approaches from the A side, it has to look through the entire A atom and its valence shell electrons to look past it and see those bound electrons in the AB bond. Well, it's going to be shielded on some level. Its electromagnetic forces are going to be shielded by the A atom and all of its electrons. And furthermore, C is not capable of forming a bond with A, and so, because we've assumed that for this example, and so that particular angle of approach is going to be very unfavorable for the reaction. Now, down here, I've shown the C atom approaching the AB molecule from kind of a perpendicular direction, pointed directly at the AB bond. In this case, down here, the C atom does not have to look through the A or the B nuclei to see the electrons in the bond. It can kind of approach them relatively closely and get a direct angle on them. That's going to be more favorable for the C atom. It's going to be able to communicate its forces better to the electrons in the AB bond from this angle than if it approaches from the A side. Over here, we're showing the C atom approaching from the B side. Again, it's going to have to look through the B atom and all the electrons in the B atom before, or the valence electron shell electrons in the B atom before it can see these electrons in the bond. So it's not going to communicate its forces the best from that position, but it is capable of forming a BC bond, so it might be possible that if this C approaches from this direction, that one of these electrons will get pulled over and you'll be allowed to form the BC bond. In short, the take-home message is that there are specific kind of geometrical requirements for every atom, or for every reaction. Every reaction involves molecules and atoms coming together and exchanging electrons. Well, there's only certain angles from which certain electron exchanges can occur. And so we have a geometric requirement on any reaction. Okay, keep that in mind. We're going to build on it shortly. The writing just essentially says what I'm orating, so if you want, you can check notes later. If you want to refresh. There are specific requirements on we just look at geometric requirements. And let me say this. It's not necessarily the case that if the C atom approaches that AB bond, that it's going to be able to simply go in and pick off those electrons, if it simply approaches it from the right angle. We show different angles. Some angles are better than others. But simple approach may not suffice to remove that electron. Again, that's because the electron is bound tightly in that AB bond. And when it's bound tightly, strong forces attaching it to the nuclei. And so if these electrons the C wants to get a hold of are attached so tightly to its AB nuclei that they can't be removed, then C is going to have a hard time getting this reaction to happen. And so, in addition to the geometric requirements, we're going to have energetic requirements on this reaction. C is going to have to not only approach the AB bond from the correct angle, but it's going to have to bump into it and deliver and transfer some of its kinetic energy to the species in order to loosen up those electrons in the AB bond. So in a collision between two species, they're moving with some velocity, they smack together. While they were moving, they had kinetic energy associated with the masses and the velocities traveling, but after the collision happens and those atoms stop moving linearly in space, all of that kinetic energy gets turned into potential energy. Well, potential energy delivered to the system can and will act to loosen up these electrons from their nuclei. We said that when we have an electron, or a negative charge and a positive charge bound close together, this is kind of a low energy state. When we put energy in, we can separate them. That's exactly what happens in this collision process. In the collision process, the kinetic energy of motion is converted into kinetic energy and potential energies of those electrons. The electrons move further away from their associated nuclei, and so they become less tightly bound. Yeah? Once those electrons are less tightly bound, then the C atom is going to be able to come in and use its electromagnetic forces to pick that electron off. So what I've shown here this is supposed to be two different collisions. In one collision, the C atom bumps into the AB bond, but it does so very weakly. And when it does that, not much kinetic energy gets transferred into the AB bond, and these electrons kind of stay exactly where they're at. Well, that doesn't lead to reaction. In this collision over here that I've tried to draw, you'll notice that the electrons from the AB bond are no longer kind of set in the AB bond. They've been pushed out to the perimeter of the atoms. Well, what's happened here is enough kinetic energy has been absorbed by the system that those electrons have been displaced from their bonding regions. Once they've been displaced from those bonds that they were in, now the reaction is going to proceed. Again, because now the electrons aren't bound tightly enough to prevent the removal. This concept is where the term activation energy comes from. We're going to use that a lot. Activation energy, you can think of, it's the energetic requirement for a reaction to proceed. It's the amount of energy that the reactant species must absorb before they can go on to product molecules. We're going to show you little graphs, reaction coordinates, where we start off at one energy level in the products, we end up in some other energy level in the reactants, but before we can get from products to reactants, we have to move over this big hill. Well, at the top of this hill, or the distance between the top of that hill and the energy level of reactants is the activation energy. It's the amount of energy that the reactants have to be increased by before the reaction can go. Okay? So we have geometric requirements, we have energetic requirements. Two key points. we said that reaction is dependent on collisions. You have to have collisions between the reactants before the reaction will proceed. Yeah? Well, that gives rise to concentration-dependent terms in an equation for rate. In short, the higher the concentration of the species are in whatever volume that the reaction is proceeding in, the more collisions that will occur between species. Yeah? So you increase concentration, you're going to be increasing the collision frequency because there are simply more species in that volume bumping into each other. And so our rate equation ends up having concentration terms. So right here, we give a generic form for our rate equation. We say that the rate is equal to some K value, which is a constant that describes the rate of reaction, times the concentration of the reactants raised to the power of the coefficients. These concentration terms are where relative amounts of species are accounted for in the rate equation. Concentration goes up, rate goes up. We're going to find that these coefficients have to do with the number of reactant species that are actually interacting in the rate determining step. We'll take a closer look at that in a moment. Okay. So for our hypothetical reaction, if we have we're looking at what is referred to as an elementary step of a reaction. An elementary step involves specific reactant species, specific product species, and a specific transition state energy barriers reaction. For our reaction, where we have the AB species and the C species coming together to interact, one AB molecule collides with one C molecule in this hypothetical situation. And so your rate is going to be dependent on the concentration of AB molecules because they're going to be involved in the collision. It'll also be dependent on the concentration of C atoms because those guys are going to be involved in the collision. Because we only have one AB species, AB molecule, in this particular collision, the coefficient for the AB molecule in the concentration terms will be 1. If, for instance, we had two AB molecules that were involved in a collision, that were required for a collision, then the concentration of AB molecules would show up in the rate law twice because we have to account for the AB concentration for two different species that happen to collide. But when there's only one species involved in that elementary step, the coefficient will be 1. Do you guys understand where the coefficients come from now? Okay. So those are our concentration dependent terms. Temperature affects the rate of a reaction. In short, when you increase the temperature on a system of matter, you increase the amount of energy that system is required to hold. So at higher temperatures, matter must take on more energy. One of the ways that it takes on that energy is kinetic energy. Kinetic energy can have different forms. It can be in the form of linear kind of travel of a species. Or linear motion. It can be in the form of vibrational motion or rotational motion. Any of those kinds of motion are mechanisms through which a molecular species can take on thermal energy, kinetic energy. What's important for reactivity and reaction rates is that translational kinetic energy the molecule stores. So as you increase the temperature, the species begin moving with greater translational kinetic energy. This does two big things. Number one, when you increase your translational kinetic energy, more collisions happen, your collision frequency increases. If we all start walking around the room at 1 mile an hour, we might not collide with each other very quickly. But if we all start running around the room at 50 miles an hour, we're going to bump into each other all the time. So an increase in your temperature is going to increase translational kinetic energy, which will increase your collision frequency. That is not the most important effect that temperature has on a reaction. Let me show you what the most important effect is. I didn't label these graphs appropriately. The first graph shows you how a velocity distribution changes when you increase temperature on a system of matter. You never have all the molecules going the same speed. Some are moving very slowly, some are moving very fast. But there's essentially a bell curve distribution at a given temperature, where many of the species will be traveling at one speed, fewer will be traveling at slow speeds, and very few will be traveling at high speeds. Yeah? When that temperature increases on the system, all of the species start moving on average at faster speeds. What that does is it stretches out that bell curve distribution. You now have fewer molecules traveling at very slow speeds. Your average speed shifts to higher velocities, and you get more molecules that are traveling at those very high speeds. Yeah? We need to think of this in terms of kinetic energy in order to talk about how this affects rate. Yes, the increased speeds do increase the collision frequency, but they do something else. Ke is equal to 1/2 mv squared, right? And so those bell curve distributions of velocity give rise to bell curve distributions of energy. Now, we said that every reaction has a certain minimum energy barrier that has to be overcome before the reaction will proceed. And largely that energy barrier is about loosening up electrons so that they can exchange bonding partners, right? The electrons associated with atoms, you got to put in enough energy to loosen them up so that reaction can occur. Down here we have two graphs. If this is the energy graph at T1, this graph that shifts to the left is the energy graph at T2. Notice that at T1, well, we're gonna draw a little V here. This is that should be P, Ke. This is the minimum amount of energy that a colliding species is going to have before the reaction will proceed. So unless a colliding molecule has this minimum amount of kinetic energy, it won't go on to form products. Notice at the first temperature, only a very small percentage of total molecules actually had enough energy to make the reaction go forward. Yeah? Well, when you increase the temperature and then increase the amount of energy that the species are carrying, and that distribution shifts over, now many more, almost half in picture electron, of the species have enough kinetic energy, sufficient kinetic energy, to make the reaction move forward. Yeah? And so the increase in temperature does two things that increase reaction rate. It increases collision frequency, but it also increases the average amount of energy exchanged in a collision. And it's that increase in the average amount of energy exchanged that has the greatest effect on the rate. Because now, more of the collision processes are actually transferring enough energy to get over that reaction barrier and move from reactants to products. Okay? Okay, so we said geometric requirements, energetic requirements, and we looked at how the temperature relates to the energetic parameters, the energetic requirements. What's next? So here's the part that you don't have to know for purposes of exams. We said that when temperature increases, the rate of a reaction increases. Yeah. The form of the rate constant K is this. It's K is equal to A e to the negative E sub A over RT. Now, temperature being in the denominator of that decaying exponential means that the larger the temperature is, the smaller the decay is of the exponential. And so what that means is that you increase T, the absolute magnitude of K ends up being larger, therefore the magnitude of the rate is larger. This A right here, it's not on this slide, but the next one. We point out that A is the geometric requirements. We said that something that has only certain angles of approach that it can react from won't react as readily as something that can function from any angle of approach. Well, in your rate law, that A accounts for those geometric or steric requirements. If a reaction has very stringent geometric requirements, if it only can react from a small percentage of the total available angles of approach, then that A is going to be very small, indicating that the rate is very slow. If a reaction proceeds very readily and can occur from any different angle, then that A will be some very large value. So your A in the K equation accounts for the geometric requirements, your T accounts for those temperature effects, and E sub A up there is your activation energy. So talk about that. We said that the activation energy was the amount of energy that you needed to put into the system before you could loosen up those electrons. Obviously, if that's a very high energy requirement, the rate isn't going to be very, very large. If you have to put a lot of energy in to get the reaction to go, then only a small percentage of your collisions are actually going to be sufficient to transfer that amount of energy. Well, with the activation energy up there in the numerator of the decaying exponential, the larger the activation energy is, the larger the decay is, and therefore the smaller the rate. So you guys don't need necessarily to be able to spit out the whole K equation, but what you do need to remember is that you've got geometric requirements, you've got activation energy requirements, and you need to remember that the temperature is going to increase the rate because of not only the increase in collision frequency, but the increase in the amount of kinetic energy that's transferred in those collisions. Catalysts. So a catalyst is something that speeds up the rate of a reaction without being consumed or used up in the reaction. We'll give an example or a couple of examples for how that can occur. But when you're looking at the reaction coordinate, the way that you can tell the reaction's catalyzed is that the activation energy, the energetic requirement for reaction drops. So you had a path that looked like this, where you had some big hill to climb. But in the catalyzed path, that hill gets smaller. Many different ways that a catalyst can function. We'll talk about that. I can't believe I record myself when I'm